Welcome to GER Hub Mathematics and Statistics lessons. In today's video, I'm going to be talking about coordinate geometry part 1. So in this particular segment of coordinate geometry, I shall start with answering the question, what is coordinate geometry? I shall also answer the question, what is a coordinate system? We shall be discussing change in coordinates, distances between 2 points, and the midpoint of a line segment. Please smash a like on this video if you like the content. Endeavor to turn on your notification button, and please subscribe to the channel by clicking the subscription button below. Endeavor to share this video if you like the content, and I'll be seeing you shortly. Geometry has been defined as the branch of mathematics which studies the properties and relations of points, lines, surfaces, and solids. Okay? But what then is coordinate geometry? Coordinate geometry is the study of geometry using coordinate points. Okay? Simple and short, coordinate geometry is the study of geometry using coordinate points. Now, there are alternative names to coordinate geometry. If you don't want to call it coordinate geometry, you could call it analytic geometry, which means the same thing, or you could call it Cartesian geometry. Aside calculus being a concept in mathematics that was invented in the 17th century, coordinate geometry is another concept in mathematics that was invented in the 17th century. So let's answer the question, who invented coordinate geometry? René Descartes invented coordinate geometry. René Descartes, who was also in Latin known as Cartesian, invented coordinate geometry in the 17th century. Now, it became the first link between geometry and algebra. His invention became the first link between geometry and algebra. Now, you will come to realize from the name Cartesian why coordinate geometry can also be called Cartesian geometry. It was named after René Descartes, who was also known in Latin as Cartesian. Okay? Now that we've answered the questions, what is coordinate geometry and who invented coordinate geometry, let us now move on to answering the question, what is a coordinate system? A coordinate system is a tool in coordinate geometry that is used for locating points in a two-dimensional surface, otherwise known as a plane, or in three-dimensional surfaces, okay? So, another name for a coordinate system is a reference system, and I'm going to be discussing these concepts immediately. So there are two types of coordinate systems I'm going to be discussing in this segment. Now the first one is called the two-dimensional coordinate system. Okay? And the second one is called the three-dimensional coordinate system. So I'm going to emphasize the two-dimensional coordinate system, although I'm going to give you a small explanation on the three-dimensional coordinate system. But my emphasis shall be on the two-dimensional coordinate system. So let's start with answering the question, what is the two-dimensional coordinate system? So the two-dimensional coordinate system is a tool for locating points in a plane. And what do we mean by plane? A plane refers to a two-dimensional surface. Okay? A plane refers to a two-dimensional surface or flat surface. Okay, so the first question I want us to know, or want us to answer in this particular segment, is what is a two-dimensional coordinate system? A two-dimensional coordinate system is a tool for locating points in a plane, otherwise known as a two-dimensional surface or a flat surface. Okay, now what other names can we call a two-dimensional coordinate system? A two-dimensional coordinate system okay, may be called 1. It may be called a 2D system for short. So you could call a two-dimensional coordinate system a 2D system. If you don't want to call it a 2D system, you could call it a Cartesian plane. Okay? You could call it a Cartesian plane. If you don't want to call it a Cartesian plane, you could call a two-dimensional coordinate system a two-dimensional rectangular Cartesian. Okay, so any of these three names can be used to describe a two-dimensional coordinate system. Now, the next question I want us to answer is, how do we form a two-dimensional coordinate system? Remember, a two-dimensional coordinate system is a tool for locating points in a plane. Now, it means if I want to locate a point in a plane, then I must put that point in a two-dimensional coordinate system. So, how do we form a two-dimensional coordinate system? It is very simple. All you have to do is to draw one real line vertically, and you would have to call this real line the y-axis. Okay? So draw one real line vertically. Of course, you know that a real line is partitioned into two by a 0. Okay? So draw a real line vertically and draw another real line perpendicular to the vertical one you've just drawn, and call this one the new real line that cuts this one at the 0. Call this real line the x-axis. Okay? Now, since both real lines cut themselves at their zeros, you would come to realize that the 0 can be called the origin of this plane. So when you put two real lines across one another perpendicularly, forming a y-axis and an x-axis, you would therefore have a coordinate system that is called a two-dimensional coordinate system. So this is an example of a two-dimensional coordinate system, an xy plane. Okay, so it can be called an xy plane. Now, if you want to locate a point in this xy plane, or this Cartesian plane, or two-dimensional coordinate system, or 2D system, any one you want to call it, how do we do that? Now, if you pick a point, say P, in this plane, remember the essence of using a two-dimensional rectangular Cartesian is to locate points in a plane. Now, if I pick a point, call it P in this plane, and I want to determine the location of P, all I have to do is to trace a perpendicular distance from P down to the y-axis. I'm going to call this point where it touches the y-axis small letter y. Now, of course, if this is 0, it means the distance from 0 to small letter y would be y. Okay? Now I'm going to also trace the distance, perpendicular distance from P to the x-axis, and I'm going to call this point small letter x. Of course, from 0 to x will give the distance x. Okay? So what I'm trying to discuss here is how to form a coordinate system and consequently use it to locate a point P. Okay? Now, what do we call this distance? What do we call this distance? This vertical distance of P away from the x-axis. This vertical distance of P away from the x-axis is called the ordinate. Okay? It's called the ordinate, or you could call it the y-coordinate. Okay? Now, there is also another perpendicular distance of P away from the y-axis, and that perpendicular distance is x. So this perpendicular distance of P away from the y-axis is also called abscissa. So you could call this perpendicular distance of P away from the y-axis abscissa, or x coordinate. Okay, now that we know that P can be located using its perpendicular distance away from the y-axis and its perpendicular distance away from the x-axis, how then do we represent P? Now, there is always a bracket containing what is called an ordered pair of the coordinates, starting with the abscissa followed by the ordinate. So if I want to locate P, knowing that P is vertically or perpendicularly away from the y-axis by a distance small x and perpendicularly away from the x-axis by a distance small y, what I'm going to do is to form an ordered pair starting with the abscissa x, the distance of P perpendicularly away from the y-axis, followed by the perpendicular distance of P away from the x-axis, called the ordinate. So this is how to locate P. So clearly you can see that P is on a location x, y, telling you that P is on a distance, perpendicular distance away from the y-axis x and a perpendicular distance away from the x-axis y. Okay, that is how to locate a point P in the two-dimensional rectangular Cartesian, otherwise known as the two-dimensional coordinate system. Okay, so that is how to locate a point. Quickly going over this, you will see that we have just talked about what a two-dimensional coordinate system is, what names it can be called alternatively, how to form a two-dimensional coordinate system, and how to locate a point P in a two-dimensional coordinate system. Okay, so I'm going to give you an example of how to locate points. I'm going to give you several points and how to locate them in a two-dimensional system. Now let us consider this example of locating the points 2, 4 and 3, 6 in a two-dimensional system and locating the point 4, 1 and 0, 3 in a two-dimensional coordinate system. So if you want to locate a point in a two-dimensional coordinate system, it is easy. All you have to do is draw the coordinate system. Okay, draw the coordinate system, the two-dimensional rectangular coordinate system. This is my y-axis and this is my x-axis. Now I'm going to put several markings here. This is obviously 0. I'm going to call this 1, 2, 3, 4, 5 and 6, and I'm going to do the same thing here. 1, 2, 3, 4, 5 and 6. Okay, now let's start with locating the first point. Precisely, let's call this point P and let's call this point Q. Let's call this point A and let's call this point B. Okay, now if you want to locate point P in this coordinate system, you would notice that x in this case is 2 and y is 4. Okay, so quickly we will trace x, perpendicularly upwards to where you have 4. Okay, so x is 2. This I'm going to trace up to this point, and I'm going to trace another perpendicular distance from 4 down to this point. So clearly this will be the point P, 2, 4. Why? It is because x from 0 to 2 is 2 and y from 0 to 4 is 4. So locating the point P, 2, 4 is done by tracing the point P down to 2 and tracing it also to 4. If you want to do the same thing for 3 and 6, Q, 3 and 6, all you have to do is to locate 3, trace 3 upward. From 3 you could trace upward. Okay, so trace 3 upward. Let us trace 3 upward to where you have 6. Okay, I'm going to do this. So I'm tracing 3 upward to where we have 6, and this will be my point Q. Okay, 3, 6. So it is that easy. Now if you want to locate the point 4, 1, A, 4, 1, all you have to do is repeat the same procedure. What is your x? In this case, your x is 4. And what is your y? Your y is 1. just like this was x and this was y. So in this case, your x is 4. So where do we have 4 on the x-axis? This is 4. And where do we have 1 on the y-axis? This is 1. So I'm going to trace this. I'm going to trace from 1 on the y-axis, since my y is 1, down to where I have 4 on the x-axis. So this will be the point A4, 1. Now, if I want to locate the point 0, 3, B03, I'm going to locate where do we have 0 on the x-axis. This is 0 on the x-axis. And where do we have 3 on the y-axis? This is 3. So this point B03 will be a point on the y-axis. So this is clearly B03. Okay? So the point is located on the y-axis at 3, meaning that its abscissa is 0 and its ordinate is 3. So that's how simple it is to locate points on or in a two-dimensional coordinate system. Okay, now you will notice that I have not accommodated any negative value in any of these problems, and that brings me to what I want to discuss finally on a two-dimensional coordinate system. Now let us see something. If I have a two-dimensional coordinate system like this, remember, forming a two-dimensional coordinate system simply requires that you partition two real lines or place two real lines perpendicular to themselves, crossing themselves at the 0, otherwise called the origin. Okay, so this forms a y-axis and this forms an x-axis. Now take note, in our consideration here, we've only considered points above the x-axis and points to the right of the y-axis. So every point on this x-axis is to the right of the y-axis, and every point above this x-axis is considered positive. Now please take note, we start with, whenever you have a two-dimensional coordinate system, a two-dimensional coordinate system brings about 4 quadrants. Okay, so there are 4 quadrants that are developed whenever you form a two-dimensional coordinate system. So this quadrant is called the first quadrant. Okay, this is called the first quadrant, and this is called the second quadrant. Okay, so we go in anti-clockwise manner. This will be called the third quadrant, and this will be called the fourth quadrant. Okay, this will be called the fourth quadrant. Now, so in anti-clockwise manner, whenever a two-dimensional coordinate system is formed, there are 4 quadrants in question. Now please take note, in this particular segment there are I'm going to be using P, X, Y, in this case in the first quadrant, to represent a point P in the first quadrant. I'm going to be using P. Now take note, when I'm using P, X, Y, I'm referring to a general point. Now if I'm referring to a specific point, I'm going to be using subscripts to my X and Y. And what am I trying to say? It means if I want to refer to a point in particular, a specific point, I may end up calling that point Px1, Y1, and I may call another point Qx2, Y2. So for as many points I have, I'm going to be using subscripts to denote them. So when I'm using this notation, take note, I am referring to specific points, okay, in the two-dimensional plane. When I'm using subscript, I'll be referring to specific points in the two-dimensional plane. But when I'm using X and Y, I'll be referring to general points. So take note, in a two-dimensional system, this is called the first quadrant. In anti-clockwise manner, this will be called the second quadrant. So going in this manner, you will have this to be the third quadrant and this the fourth quadrant. Now what I want to show you is that in the first quadrant, your ordinate y and your abscissa, both of them are always positive. Okay, so if you have a point P in the first quadrant, this could certainly be what you have. Okay, this could be what you have. So if this is the point P, this is clearly what you have. Now this distance, of course, this distance is x, and this distance, this perpendicular distance, will be y. Okay? Now we could move into the second quadrant, and moving into the second quadrant would imply that something has to change. Now clearly, if you bring P into the second quadrant, then it implies that your y being your ordinate will still remain positive, so this will remain positive y. But because it has come into the second quadrant, note that the second quadrant is on the other side of the 0 for the x-axis, and every point to the left of the 0 on the x-axis will be negative. So it means that in this case we will be having minus x. So when P is a point located in the second quadrant of a two-dimensional rectangular Cartesian, then the ordinate remains positive while the abscissa becomes negative. Now if we move this, in this case, let me quickly specify, if this is my P, then note that clearly the abscissa becomes negative x, okay, while the ordinate remains positive y. Now let us move P into the third quadrant and see what happens. Now in the third quadrant, you will notice that P, if I bring my P over here, my abscissa will be negative and my ordinate will also be negative, because below the y-axis, below the 0, every point is negative. Every number below the y-axis is a negative number, is a negative real number, and every point to the left of the x-axis is also a negative real number. Now we could also bring P into what is called the fourth quadrant, and if we bring P into what is called the fourth quadrant, what would you notice? You will notice that x is positive but y is negative. Why is x positive? X is positive, your abscissa is positive because it is on the right hand side of the x-axis, that is the right hand side of the 0, but it is negative, your ordinate is negative because it is still below the y-axis, below the 0 on the y-axis. So what I want you to know is that there are 4 quadrants whenever there is a two-dimensional rectangular Cartesian form, okay? And these 4 quadrants are taken in anti-clockwise manner, starting from the positive x-axis. Now as you move from quadrant to quadrant, the abscissa or the ordinate may become negative, as the case may be. Now I'm going to show you an example on how to locate points on different parts of the two-dimensional coordinate system aside the first quadrant, okay? So let us consider that now. So let us consider this example number 2, which demands that we locate the points P minus 3, 1, Q minus 2, minus 6, and R 4, minus 2, okay? So for us to get that done, quickly put up your two-dimensional rectangular Cartesian, okay? So you have your positive y-axis, you have your positive x-axis, okay? Now let's see, the points we want to locate, take note, are not in the first quadrant. The points we want to locate are in the second, third, and fourth quadrant. So there is a point P on minus 3 and 1. So I'm going to look at this in this manner. 1, I'm going to call this 1, 2, 3, 4, 5, and 6. I'm going to do the same thing below. 1, 2, 3, 4, 5, and 6. Now take note, because all these are below, all these points are below 0 on the x-axis, I'm going to put a minus to all of them, okay? Because they are all negative real numbers. Now I'm going to put this 1, 2, 3, 4, 5, and 6. Okay, and I'm going to do the same thing here. Minus 1, since it is to the left of the x-axis or the left of the 0. Minus 2, minus 3, minus 4, minus 5, and minus 6. Okay, now having done that, let us now locate the points. The required points are P minus 3, 1, Q minus 2, minus 6, and R 4, minus 2. So what am I going to do here? I'm going to start with the first one, this. Take note, in this case, my x is negative and my y is positive. So I'm going to come to the negative x-axis and trace minus 3 upward to where you have 1. So this is where you have 1 on the y-axis. So I'm going to trace this upward to this point where we have 1. And I'm going to call this P minus 3, 1. Because my abscissa is negative, but my ordinate is positive. And what is your ordinate? 1. What is your abscissa? Minus 3. So that specifies or locates the point P. Now coming to Q is on minus 2, minus 6. So on the negative side, I'm going to trace minus 2, my abscissa, down to where you have minus 6 on the y-axis. So this will certainly be the point Q on minus 2, minus 2, minus 6. So all I had to do was to trace from minus 2 down to where you have minus 6, okay? And that will give the point Q. Now Q is clearly in the third quadrant. Coming to R can be located by noting its abscissa to be 4. So where do we have 4 on the positive x-axis? This is 4, okay? Now what do we have as its ordinate? Minus 2. This is minus 2. So I'm going to trace minus 2 to 4, or minus or 4 to minus 2, and this will give me R 4, minus 2. Okay, so that is how to locate those points on the two-dimensional rectangular Cartesian. So you don't just locate only points in the first quadrant where the abscissa and the ordinates are positive. You could also locate points in any of the other quadrants. Okay, now that brings me to what I had mentioned earlier on. I had earlier mentioned that I'm going to be talking about a 3D system briefly. Okay, so let us now consider a three-dimensional system. So let's consider a three-dimensional coordinate system. Okay, so let's start with stating what it is. A three-dimensional system is a tool in coordinate geometry for locating points in a three-dimensional plane. Okay, so if you want to locate points in a three-dimensional plane, it's a tool. You'll be using a three-dimensional coordinate system. So it is a tool in coordinate geometry for locating points in a three-dimensional plane. Now, how do we get a three-dimensional system formed? All you have to do is to place three real lines across themselves at right angles. Okay, so the first thing I'm going to do this. Okay, so you watch what I'm doing. I'm going to place one real line, and I'm going to call this one the x or the y axis. Okay, I'm going to place it at 90 degrees. I'm going to place another real line, okay, called the x axis at 90 degrees to the y axis. Okay, so my x axis is perpendicular to my y axis. Now I'm going to draw a third real line. Take note, all of them converge again at their zeros, okay? The zeros of each real line. And that will give the third line, the third real line, which I'm going to call the Z axis, okay? So all of them converge at the origin again, which happens to be the zero of each line, okay? Now, this is how to form a three-dimensional coordinate system. Remember, our emphasis in this video or in this lecture is to talk about the two-dimensional system, but I had promised earlier on to describe a three-dimensional system. Now, this is how to form a three-dimensional system. Of course, above the zero on the z-axis, all the numbers are positive, all the real numbers are positive. Below the zero on the z-axis, all the real numbers are negative. Now, to this side of the y-axis, all the real numbers are positive. Behind the y-axis, behind the zero of the y-axis, all the real numbers to this side are negative. To the left or to the right of the x-axis of the zero on the x-axis, all the numbers are positive. To the left of the zero on the x-axis, all the numbers are negative. So if I want to locate a point, say P, let's try locating a point P. Now, unlike the two-dimensional coordinate system where we used an ordered pair, we would be using an ordered triplet here, okay? So for you to locate a point in a three-dimensional coordinate system, you will be using an ordered triplet. So this is P. I'm going to use another triplet of X, Y, and Z. Now, how do we get X, Y, and Z? The first thing you're going to do is to trace P vertically or perpendicularly to Z, okay? So I'm going to trace this. You can trace P perpendicularly to Z, okay? So trace it perpendicularly to Z. Now, trace it down, trace your P down to a point in the XY plane. Now, notice that the XY plane is perpendicular to the Z plane, okay? So, for you to locate a point P in a 3D system or a three-dimensional system, all you have to do is to pick the point P and trace its distance, its perpendicular distance to Z, then trace it down perpendicularly to the plane, the XY plane, and then trace its points perpendicularly to Y and perpendicularly to the X axis. So this is what you'll have. Now, this is clearly small z. This distance is small z. This distance on the y-axis is small y. And this distance on the x-axis is small x. Okay? So, this describes briefly what we regard as a three-dimensional coordinate system. But in this video, my focus will be on the two-dimensional coordinate system. Now, having said that, let us move ahead to the next thing I want to discuss, which is the distance, how to change coordinates in a coordinate system, in particular a two-dimensional coordinate system. So to change coordinates in a coordinate system, all you have to do is to use what we call increments, okay? So I'm going to put up a coordinate system where I have my x-axis and I have my x-axis and my y-axis, okay? So this is my y-axis and this is my x-axis. Now, let's assume that I have a point, a specific point. Recall that I have told you earlier on that I could have a specific point px1, y1, okay? And that means that I have this, okay? If you recall what we've done, so this is clearly y and this is x, meaning that the distance from the origin to this point is x and the distance from the origin above the y-axis to this point is y. Okay, now it is possible that P can describe a moving particle or a moving object such that from this location P there could be a movement of P in this particular two-dimensional coordinate system down to another point, say Q. Okay, so let's call this point Q. Now, because this is another specific point, I'm going to call this x2, y2. Now, if you trace this down, you clearly see that this is because Q is only on x2, y2 because its perpendicular distance down to away from the x-axis is what can be regarded as y2. Okay, so its perpendicular distance away from the the x-axis is y2, whereas its perpendicular distance away from the y-axis is x2. Okay, so this is x1 and this is y1. Okay, now let's look at it again. So what is actually going on here? You will notice that this can be likened to having a particular object or a person moving from this point down to a new point here. Okay, now when a person moves within the two-dimensional coordinate system from one point, say P, to another point, say Q, what that person has done, or what that object or particle has done, is changing coordinate system. Now you will notice that changing coordinates rather. So you will notice that P, the object here, has changed its coordinates from P x1 y1 through its movement to a point Q x2 y2. Now you will notice two things are going on here. Now what is actually going on is the idea of increment. Now notice something. I could form I could draw a line segment joining P to Q. Now you would notice, let me form this. Okay, now you will notice what is going on here. Now x2 from this diagram is clearly greater than x1. So x2 is greater than x1. And notice again that y2 is also greater than y1. Now, notice that from this point, the 0 up to y2 gives y2. And from 0 up to x2 gives x2. Okay? Now, notice again that from 0 to y1 gives y1, and from 0 to x1 gives x1. Now, what has actually happened in the movement of this object from a point P to a point Q? You will notice that an increment has taken place. Now, we would use the delta to represent an increment. Okay? So, the movement along the x-axis was from x1 to x2, and this is the change in the movement. So if this was x2, the gap between x1 and x2, we shall call that gap delta x. Okay, now similarly, this is from 0 to y2. This is y2. Okay, now you will notice that there is a gap between y1 and y2, and that gap we shall call delta y. So this gap is called delta y, and it is equal to y2 minus y1. The gap also here is called delta x, and it is equal, delta x is equal to x2 minus x1. And what does delta x represent? It represents an increment in the x movement from x1 to x2. Okay, so the x movement, an increment in the x movement or distance from x1 to x2, and delta y also represents an increment in the y movement, okay, from y1 to y2. So whenever there is an increment, there is every tendency that coordinates have been changed by a particular particle or object, okay? So that could be above or it could go below. It could go negatively, it could go positively. So the same way we've moved from P to Q, we could also move from P to a point downwards, okay? So what is responsible for this is the idea of increment. So whenever there is a change in coordinates, there is always an increment. The increment could be negative, the increment could be positive. So please take note of that. Now, as an example, let's call this example number 3. What is the increment from P21 to Q35? What is the increment? Okay, now the increment is clearly the distance moved, the change in the distance moved along the x-axis, as well as the change in the distance moved along the y-axis. So let's see what the increment is. The change in the distance moved along the x-axis is the x increment, and the change in the distance moved along the y-axis is the y increment. So let's see. So for P21, this will be x1 and this will be y1. For Q35, this will be x2 and this will be y2. Okay, so there was a change in coordinate from P to Q. Now let us calculate quickly the x increment. Remember, the x increment is denoted by delta x. All you have to do is to compute x2 minus x1. So it is that easy. If you want to compute the x increment, compute x2 minus x1. Now what is your x2 in this case? Your x2 is 3. What is your x1? Your x1 is 2. So what is the increment? Delta x is 1. Again, if you want to compute the y increment, it will be the change in movement or the change in distance moved along the y-axis, and that will be y2 minus y1. So what would that give us? Our y2 is 5 and our y1 is 1. So that will give us 5 minus 1, which is 4. Okay, so that is how easy it is to compute the increment. Let's take another point. What if I asked, as an example number 4, for the increment? Compute the increments from P minus 21 to Q 5 minus 6. Now, all you have to do again is to note that this is your x1, this is your y1, this is your x2, and this is your y2. Okay, so the increment along the x-axis will be x2 minus x1, which will give us 5 minus 2 in this case. Take note. So it will be 5 minus 2. Why? This minus here remains, but x1 is minus 2, and that will give you 5 minus times minus is plus, so that gives you 5 plus 2, which is 7. Now for the y increment, this will be y2 minus y1, and that will give you, what is your y2? It is minus 6. What is your y1? Your y1 is 1. So this will be minus 6 minus 1, which gives you 7. Okay, so that will give you minus 7 rather. So that is how to compute the increment. Now let's move to the next segment, where we shall be discussing the distance moved between 2 points. Okay, the distance between 2 points. So for the distance between 2 points, let's see how that is done algebraically first, before taking an example. So for you to compute the distance between 2 points, I'm going to put up a coordinate system here, a two-dimensional coordinate system. Okay, So let's take a first point here. So this is my y-axis, this is my x-axis. Now I want to follow what is being done. So we want to compute the distance between 2 points. Now I'm going to call this point here P x1 y1 because it is a specific point, remember. Now let's assume that P changed its coordinates to another point Q. Okay, so this is a point Q on x to y2. Okay, now clearly this forms a line segment PQ. Now if you want to compute the distance between 2 points, let us start with understanding what is actually going on here. So I'm going to trace this. I'm going to trace this down to x1, and I'm going to trace this perpendicularly down to x2. Okay, now I'm also going to trace this perpendicularly to what you call y1. Okay, that's the initial movement or the initial point on y. That's the initial ordinate. And I'm going to trace this down to the second ordinate on y, which is y2. Okay, clearly this distance between y2 and y1 is changed in y. Okay, and this distance between x1 and x2 is changed in x. Okay, because the total distance from here, from 0 to x2, is x2, and the total distance from 0 to x1 is x1. So clearly change in x is x2 minus x1, and change in y is y2 minus y1. Now if you extend this line, you end up forming a right angle triangle. So let's call this point here on the right angle triangle, if this is P, this is Q, let's call this point R. Okay, now what is this distance QR? The distance QR is y2 minus y1, okay, which is change in y. And the distance PR, this distance PR is x2 minus x1, which is change in x. Okay, now what we want to find is the distance moved along this line segment from P to Q, not these ones, not QR. We are not interested in QR, the distance QR, neither are we interested in the distance PR. We are interested in the distance moved along PQ from P to Q. Okay, now if you bring out this right angle triangle we have formed, the right angle triangle PQR, if you bring it out, so let's bring it out here, clearly you would notice that we have this, okay, such that this is change in x equals x2 minus x1, and this is change in y, which is equal to y2 minus y1. This is P, this is Q, and this is R. So since our interest is in knowing what PQ is, the distance along PQ, you would notice that since this is a right angle triangle, then Pythagoras Theorem applies. So what are we going to do? Clearly, you would notice that PQ squared is equal to, that is hypotenuse, PQ is hypotenuse squared, will be equal to adjacent squared plus opposite squared. Okay, so you could take your adjacent to be any of these, that is change in x or change in y. So I could call this change in x all squared plus change in y all squared. And that means taking, if I choose to now make, if you make PQ the subject of formula, then you would obtain a formula for computing the distance along any line segment in a two-dimensional coordinate system. And that will be the square root of the positive square root of change in x all squared plus change in y all squared. Now we could also choose to write this as PQ equals the square root of what is change in x. Change in x is x2 minus x1. So I'm going to put x2 minus x1 all squared. What is change in y? It is y2 minus y1 all squared. So this formula will be used to compute the distance between 2 points on the line segment. Now take note, in coordinate geometry, for you to obtain the distance, you don't need to actually draw this diagram all over again. Let's consider this example on the distance between 2 points. So I'm going to call this should be example number 4, if I'm correct. Okay, if I'm not correct, please pardon me, but this should be example number 4. Now, obtain the distance or the distances between the pairs of points. A, we want you to obtain the distance between a point P on 2, 4 and another point Q on 1 and minus 3. B, we want you to obtain the distance between R, minus 1 and 6, and S, 2 and 0. Okay? Then let's take a third point, C. We want you to obtain the distance, let's say A, 4 and 2, and B, 3 and 1. Okay? So I want you to quickly get this done. I'm going to do A. I'm going to solve problem A and problem B, but problem C is for you. Now get your answer for me and drop it in the comment section. When you get it done, I would want to see your comment in the comment section. Okay, so do that for me. Now let's get done A and B. So I'm going to call this my solution. According to the formula, we want for A, we want to know the distance PQ. So the distance PQ will be the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Okay, so what is your x2? Your for P24, I'm going to call this x1 and I'm going to call this y1, and my q, which is 1 minus 3, I'm going to call this x2 and I'm going to call this y2. Now the good news is, whichever one you choose to be your x2 and y2, or your x1 and y1, the answer remains the same. Okay, because there is a square there that changes every negative to a positive. So for PQ, the distance PQ will be the square root, okay, of x2, which is in this case 1, minus x1, which is 2 all squared, plus y2, which is in this case minus 3, minus y1, which is 4 all squared. And that will give us the square root of minus 1 all squared plus minus 7 all squared. And that results in the square root of 1 minus 1 squared is 1, plus minus 7 squared is 49. So that gives us the square root of 50 as the distance between the point P and Q. Now let us obtain the distance between the points R and S. Remember, the one between A and B is for you, and I want to see your comments, your answers in the comment section. Please do that for me and drop your comment in the comment section. I want to see what you come up with. Okay, so I'm going to for the distance between RS, again the formula remains x2 minus x1 all squared plus y2 minus y1 all squared. So what is your x2? So I'm going to write here, this is R is on minus 1, 6, and S is on 2, 0. Okay, so clearly this is your x1 and this is your x2. This is your y1 and this is your y2. So that will mean the distance RS will be the square root of x2, which is 2 minus x1, which is minus 1 already, all squared, plus y2, which is 0 minus y1, which is 6, all squared. So that will give you the square root of 2 minus minus 1 is 2 plus 1. So that will be 3 all squared, plus 0 minus 6 is minus 6. So that will be minus 6 all squared. So square root of the square of 3 is 9, plus the square of minus 6 is 36. So this will give you the square root of 45 when 9 adds to 36. So the distance between R and S is 45. So get that done. The distance between A and B as I've given you, and drop your comment in the comment section. The next thing I want to do in this video is to go straight into the midpoint of a line segment. Okay, the midpoint of a line segment. Now guys, for the midpoint of a line segment, let us consider this coordinate system, the two-dimensional coordinate system, where we have a line segment joining the point P on x1, y1 to the point Q on x2, y2. Now, what is our interest here? Our interest is to obtain the coordinate at a point that is certainly the midpoint of this line segment. So, being the midpoint of the line segment means that r, x, y, this general coordinate here, is halfway between P and Q on this line segment, joining P to Q. Okay, so what we want to do is to obtain the exact coordinate of R. How are we going to do that? Now let us quickly do what we've done earlier on. Okay, so if this is P, tracing the point down to the x-axis gives me x1, tracing the point R to the x-axis gives me x, because that's the abscissa, and tracing this, the point Q, down to this point gives me x2. Now if I repeat the same procedure for P, tracing it perpendicularly to the y-axis, this will give me the ordinate y1. Tracing this to the y-axis gives me the ordinate y, and it gives me the ordinate y. Okay, and tracing this to the y-axis gives me the ordinate y2. Okay, now I could complete these lines, I could complete these perpendicular lines, and this would give me a figure like this. So let us name these points. Clearly this is a right angle, this is a right angle, this is a right angle. So let's call this point, we've used P, Q, and R. Let's call this S, T, and let's call this U. Okay, so let's call this point U, let's call this point T, let's call this point S. Now what is our interest? We want to obtain the exact coordinate of the point R, X, Y. Now for us to get that, we must note the following. Now you would note that there are three triangles in question here. So let me quickly bring out those three triangles. There are three triangles in question. The first being the triangle P, the biggest triangle PQT. Okay, PQT. There is another triangle that I want you to take note of, and that triangle is triangle PRU. This triangle PRU. And finally, there is another triangle, all of them being right angle triangles. Okay, and that triangle is RQS. So there are three right angle triangles, with one of them being the biggest and the mother triangle to these other right angle triangles. Now, why am I bringing out these triangles? You will notice that these triangles are similar. Okay, they are similar. Now, why are they similar? They are similar in the sense that they are all right angle triangles, although they are not equal in length. They are almost of the same shape. They are all right angle triangles, and clearly because of this, you would notice that if PQT, okay, so I'm going to put it here, note that triangles PRU and RQS are similar to the model triangle PQT. Okay, and because that is so, you would come to realize that if this triangle PQT is similar to the component right angle triangles PRU and RQS, then the following becomes obvious. Okay, the following becomes obvious. What becomes obvious is that PR, the ratio of PR to RQ will be equal to the ratio of PU to UT. Okay, that implies that PR all over RQ will be equal to PU all over UT, and that's because they are similar. Now take note that PR is equal to PU. PR is equal to RQ. And why is that so? It is because we have assumed that R is the midpoint of the line segment PQ. So it definitely means that by that assumption, PR is equal to Q and to RQ. And what that means by implication is that if PR is equal to RQ, then because the triangles are similar, then PU must be equal to UT. So it means that PU is also equal to UT. Now, based on that, you will come to realize that the gap, if PU is equal to UT, then it means the gap between U and T, which is x2 minus x, must be equal to the gap between P and U, which is x minus x1. And that implies that x2 minus x is equal to x minus x1. And if you take like terms, you end up having that 2x, when this x comes here to add to this x, it becomes 2x. And 2x will be equal to x1 plus x2, which implies that making x the subject of formula gives us x1 plus x2 all over 2. Okay? Now, similarly, for the sake of similarities between the triangles, you will notice also that PR, the length of PR all over RQ is also equal to this ratio, that is QS all over ST, because the triangles are similar. And that implies, this also implies that PR equals RQ gives rise to the implication, it gives rise to the implication that QS should be equal to ST. Okay? Now, what is the length of QS? It will be the ordinate y2 minus y, and that is y2 minus y. What is the length of ST? It will be the ordinate y minus y1. So since they are equal, then it means that y2 minus y will be equal to y minus y1. And making y the subject of formula implies that taking like terms will give you 2y equals y1 plus y2. And that means that y will be equal to y1 plus y2 all over 2. Now, what have we been able to achieve? We have been able to achieve getting this particular coordinate r, the exact values of x and y for the coordinate r, okay, or for the point r in the two-dimensional coordinate system. So it means that we've been able to establish that rxy is equal to r. Instead of putting x, we now have the exact value of x should be the addition of x1 to x2 divided by 2, and the exact value of y should be y1 plus y2 all over 2. Okay, so whenever you want to get the midpoint, it implies that all you have to do is to take the average of the abscissa of the 2 points on the line segment. If you want to obtain the midpoint of a line segment, take the abscissa, take the average of the abscissas of the 2 points on the line segment, okay, and then take the average of the ordinates of the 2 points on the line segment. Okay, so let's use an example to illustrate that. So obtain the midpoints M1 xy and M2 xy of the respective pairs of points. So the first midpoint is for the pair here A24 B53, and the second midpoint is for the pair here C10 and D23. Okay, so let's get that done. For us to get that done, all we have to do here is to say as our solution M for number 1, M1 xy, which is the midpoint of these two pairs here on the line segment. We would have this to be M1 x1 plus x2 all over 2 and y1 plus y2 all over 2. Now for this point A24, this will be your x1, this will be your y1, okay? And for the point B53, this will be your x2 and this will be your y2. Now putting that into the expression here, or the formula, gives you M1 x1 is 2 plus x2 is 5 divided by 2, comma 4 is your y1, so that will be 4 plus your y2 3 all over 2, and that gives us the midpoint, required midpoint M1 to be 7 over 2, 7 over 2. Okay, now if you come over to the second midpoint you are required to get, then you would have M2 x comma y equals M2 x1 plus x2 all over 2, y1 plus y2 all over 2. Okay, now for the point C10, this will be your x1 and this will be your y1. Okay, then for the point D23 on that line segment, this will be your x2 and this will be your y2. Now what would your midpoint be? It will now be M2 x1 is 1 plus x2 being 2 divided by 2, comma y1 is 0 plus y2 is 3 divided by 2, and that will give you M2 3 over 2, comma 3 over 2. So it is that easy to obtain the midpoint of the line segment. Now please, I'm going to give you this as a task to get done. Do this also in addition to the task I gave earlier, and please get your answers to me in the comment section. I'll be waiting to see your answers in the comment section. Please don't fail to get it done. Give me a response to this particular problem I'm going to give you in the comment section. So obtain the midpoint of the line segment AB, where A is the point half 2 and B is the point 2, 3. So get this done and send your comments to me in the comment section, and I'll be seeing you in my next class on this particular topic. Do well to subscribe to the channel if you haven't subscribed to the channel. Smash a like on this video if you like the content, and please endeavor to share this video to your friends, share this video to your colleagues, and do well to subscribe to the channel if you haven't subscribed. And I'll be seeing you in my next class. Thank you very much.